Welcome to the Chem 1A pre-lab lecture for Experiment 13, Redox Titration. This experiment is designed to introduce you to the techniques, skills, and calculations that you will need to master for your lab practical exam. The learning objectives for today are to understand and apply the technique of volumetric analysis. The type of volumetric analysis we will be doing is called titration, and is useful for determining the concentration of an unknown solution. We will also introduce you to the concept of redox chemistry, or reduction-oxidation chemistry. There are two major parts to this experiment. In part 1, you will determine the exact concentration of a dilute solution of potassium permanganate through standardization. In the second part, you will use your standardized solution of potassium permanganate to determine the percent weight by weight of oxalic acid in an unknown mixture. There are a number of terms that are specific to titrations that you will need to become familiar with. First, the titrand is a solution of unknown concentration. The titrant is a solution of known concentration that we will use to react with our titrand to determine its concentration through a known reaction. The equivalence point is when the amount of titrand added completely consumes the titrant, and so it's when we reach the molar equivalency of the two reactants. Endpoint is when there is a color change that can indicate that the reaction has reached its equivalence point. At the endpoint, the titrant is typically a little bit in excess, and that is why we see the color change. Titration error is this measure of the excess of our titrant, so it is the difference between the endpoint and the equivalence point. Titrations are performed to determine the concentration of a particular compound in solution. The setup for a titration always uses a burette and an Erlenmeyer flask. The solution of known concentration is usually added to the burette. The sample of known volume but unknown concentration is usually placed in the Erlenmeyer flask. The titrant in the burette is slowly added to the titrand in the Erlenmeyer flask until the chemical reaction between the two reaches completion, and we can see this through the endpoint and assume that we have surpassed the equivalence point. In redox chemistry, electrons are transferred from one element to another. The element that receives electrons is called reduced, and the element that loses electrons is called oxidized, and these two reactions are always paired. You might use the acronym OIL-RIG to help you to remember the definition of these terms. OIL stands for oxidation is losing, meaning oxidation is losing electrons, and RIG, reduction is gaining, so the element that's reduced gains electrons. In today's titration, you'll be looking at the reduction of the manganese cation. In potassium permanganate, manganese exists in its 3+ transition state, and through reaction with oxalic acid, it is reduced to manganese in its 2+ oxidation state. The electrons that are donated to this manganese come from oxalic acid, and so the oxalate anion of oxalic acid is being oxidized to carbon dioxide. This is an excellent reaction for using in titration because the 3+ transition state of manganese is a dark purple color, whereas the 2+ transition state is colorless, and so we can use this natural color change to determine when our reaction is completed. It's also important to note from the reaction that I've given you here that the molar ratio between the amount of permanganate and oxalic acid is a 2:5 ratio, meaning for every 2 moles of permanganate added, 5 moles of oxalic acid are consumed. In today's experiment, we will have potassium permanganate in our burette, and we will add it to oxalic acid in our Erlenmeyer flask. As I mentioned, the permanganate will begin as a dark purple solution, and when it reacts with the oxalic acid to form the reduced manganese cation, it will become colorless. Once all of the oxalic acid has been consumed by the added permanganate, additional drops of Mn3+ will not be converted to colorless, and so we will see this as a light pinkish color. This will be our end point. A volumetric analysis, or titration, can really be thought of as an exercise in limiting an excess. The titrant, which is in your Erlenmeyer flask, is the limiting reagent, and we are adding our titrant from our burette until we consume all of that limiting reagent. In this manner, we use the volume of the titrant together with its molarity to figure out the moles of titrant, and then using the stoichiometry of the known chemical reaction between titrant and titrand, we use the molar ratio to find the moles of titrand in our limiting reagent. The concentration of the limiting reagent is simply the number of moles that reacted with our titrant divided by the volume that our limiting reagent was in. So, in order to determine the concentration of an unknown solution, we begin with a solution of known concentration. We add that solution to our unknown until we reach an equivalence point, then use the molarity of the known solution times the volume dispensed to find the moles. Moles per liter times liters equals moles of titrant. We then refer to our balanced chemical equation and to use the molar ratio to convert from moles of titrant into moles of titrand. In the final step, we consider the moles of titrand that we've calculated and divide it by the volume that we initially put in our reaction flask, and this gives us the moles per liter of titrand. As I mentioned, the first portion of the experiment is to standardize the potassium permanganate solution and determine its exact concentration. You will be given a stock solution of potassium permanganate with only 1 sig fig of concentration value. You will dilute this solution to an approximate concentration and then use a known amount of oxalic acid to determine the concentration of your diluted permanganate solution. The calculations are done as follows. First step is to determine the moles of titrand that you added to your Erlenmeyer flask. So in specific, for this experiment, you would take the known concentration of oxalic acid that's provided for you and multiply it by the volume that you put into your Erlenmeyer. This will equal the moles of oxalic acid. The next step is to use the molar ratio to find the molar equivalent of titrant. So here we would convert from the moles of oxalic acid using our 2 to 5 molar ratio of 2 moles of potassium permanganate for every 5 moles of oxalic acid. We could determine the moles of potassium permanganate. You would then divide the moles of titrant by the volume that you delivered out of your burette to find the molarity of the potassium permanganate solution. So the moles of permanganate, which was determined based on the oxalic acid consumed, divided by the volume that you delivered out of your burette, will equal the molarity of potassium permanganate. With the values that I used in my practice calculations, I found that the concentration of my potassium permanganate solution was 0.0182 molar. You should take special care with your significant figures when doing these types of calculations. Remember that the number of sig figs is going to be limited by the known concentration of your titrant and by your volume measurements. The burettes that you will be using have gradations down to the 0.1 milliliter, and so with a guess between the smallest gradations, you should be able to have 2 decimal places in all your volume measurements. You will be deducted points in your lab practical if you do not use the correct significant figures. In the second part of your experiment, you will use your standardized potassium permanganate solution to determine the percent oxalic acid in an unknown sample. The titrations are conducted in the same manner, and the calculations are very similar as well. You will begin by determining the moles of titrant used. In this case, we now know our concentration of potassium permanganate. We found it when we standardized it. And so we will use the known concentration of permanganate and the volume of permanganate that we deliver out of our burette to find the moles of potassium permanganate. The next step is to use the molar ratio to convert between moles of permanganate and moles of oxalic acid. So make sure you have your molar ratio arranged in the right direction so that moles of permanganate will be on the top and then on the bottom so it cancels out. So moles of permanganate times 5 moles of oxalic acid for 2 moles of potassium permanganate will give you the moles of oxalic acid. Once we have the moles of oxalic acid, we need to convert to grams because the objective is to find the concentration in percent weight per weight. So we will use the molecular weight of oxalic acid and the moles that we calculated from our reaction with permanganate to determine the mass of oxalic acid that was in our sample. We then determine the percent weight by dividing this mass of oxalic acid by the mass of the sample that we initially put into our Erlenmeyer flask. So if I take, for example, I had 0.0710 grams of oxalic acid from my titration data, and my initial sample weighed 1.234 grams. I would divide that and multiply by 100, and my final concentration would be 5.56% weight per weight using the correct sig figs. During this experiment, you'll be working with your lab partner. However, for the lab practical, you'll have to work alone. So it's important that you master the techniques yourself and take turns with your lab partner, reading the burette and swirling the flask and judging the endpoint. In order to get a very accurate endpoint, it's important to always keep the titrant solution mixing while you're adding the titrant. Initially, have one lab partner work the stopcock of the burette while the other lab partner swirls. But as you become more adept at this, try to do both tasks yourself, since you will definitely be doing them yourself during the lab practical. Placing white paper underneath your Erlenmeyer flask can really help in judging when you've reached the endpoint, especially with the dark countertops that we have in our Chem 1A labs. For the best titration, we want to start at an endpoint with a very slight pink coloration, as shown on the left here. If your solution looks more like the solution on the right, you have overshot the endpoint. This is not too big of a deal if it's your first titration, but you want to get your replicates as close to the light pink color as possible. In order to achieve this light pink coloration, you need to add only a fraction of a drop from your burette at a time. To add a fraction of a drop, spin the stopcock a complete 180 degrees. This fluid motion with your hand will result in less time with the stopcock being open than if you were to open it by turning 90 degrees and then back the other 90 degrees. It's important with this specific redox reaction that at the beginning of your titration you add the potassium permanganate solution only very slowly. This pertains to the first 3 to 5 mils of your titration. If you add the permanganate solution too quickly at the beginning of the titration, you will end up forming manganese oxide. Manganese oxide is a brown solid and will precipitate and ruin your titration. It's also important to always read the level of your burette with your eye at the level of the liquid, as indicated in the diagram here, where the eyeball is directly across from the level of the solution. Potassium permanganate is a rich purple color and easily stains skin and clothing, so make sure you're wearing gloves and button up your lab coat to protect your clothes. Also, oxalic acid is an irritant, so you want to avoid breathing any of its dust and promptly sweep up any spills. Please take every advantage to Get assistance with this experiment and the write-up from your lab instructor, grad student TAs, the SI leaders, and from your classmates to ensure you're very comfortable with all of the calculations and techniques involved in this experiment. When it comes time for the lab practical, you will not be allowed to ask your instructor for any advice or assistance on calculations. Happy titrating!